In this video, we'll look at probability of compound events. We'll talk about what that means. And just a heads up, within this video, there is going to be a lot of discussion about vocabulary. And it's worth assigning some vocab and some terms to these. That way we can all talk about the same things. However, when you're actually solving the problems, it's not so much that you're going to need to know what the vocabulary is, but you're going to have to know what the consequences of it are. And there's a lot of these, since they are so intuitive, to where you may not even need to know about the vocabulary to solve the problem, but you do have to be very careful in what they are asking. So let's talk about compound events. We've talked about single events. So a compound event is you're looking at two or more events. So like example, if I flip a coin twice, or if I roll two dice, I'm essentially doing two statistical events, and I'm looking at each one individually, but I may, in this point, look at what happens when I'm rolling two things. So like if I'm looking at a dice, what's the probability that if I roll two standard six-sided dice, that the sum of the numbers will be 7? And that is a little bit more difficult to answer than, okay, if I have just one die, what's the probability that it's a 4? Notice how it's a little more nuanced in that I have two or more things to consider here. That's what a compound event is. So before we talk about compound events and how to calculate the probability, there is some vocabulary and some things we need to review. Let's talk about and or. And we've talked about these before in a mathematical sense, in that and is what two sets would have in common, and or would be, and remember in mathematics we're talking about the inclusive or. It could be in just one set, just in the other set, or in both. So if we're looking at a Venn diagram just in general, let's say this is the probability, or this is A, and this is event B. And we are just looking at the middle. Or could be over here, could be just in B but not in A, and it could be in the middle. We're looking at the inclusive or in this case. So keep that in mind. We're talking about if we're looking at, okay, what's the probability that I have a 6 on one standard die and I flip tails on a coin versus or. There's a difference there. It's going to affect the probability. The or is usually going to increase your chances versus if it was an and we'll talk about what those mean. So let's have a quick discussion about notation. Just some things that ways the statisticians write things. If I'm looking at the probability of A and B, meaning what's the probability that A happens and B happens? So like in the example of a coin and a die, what's the probability that I roll a 4 on a die and flip tails on the coin? A would be rolling a 4 and B would be getting a tails on the coin. So there's a couple ways you can write this. And we're looking at, you can use a shorthand. So you can write out the word like I did there between the two. Another notation that statisticians will use is this upside down U, meaning the intersection of A and B. Or, of course, you can just use probability of A and B, the shorthand for and. All of those are the same thing. It's just a way of making it easier on yourself so that way you can understand what they're talking about. If we're talking about or, another notation that statisticians will use is probability of A and then an actual just big U and then B. The union of A and B. What's the probability that it falls in either set, in either possibility? So just a quick note on notation. That's one way the statisticians will write things to save themselves a little writing. I just want you to be aware of it. You don't necessarily have to use it. Okay, so continuing on with our vocabulary. Let's talk about independence in terms of events. So what independence means is one event, or how one event could affect another. So if two events are independent, the first independent, or the first event, does not affect what happens on the second. So the first will not affect the second. Meaning, okay, if you think about an example here, if I flip a coin and roll a die, well, regardless what happens on the coin, it's not going to affect what happens on the die, and vice versa. If I roll a 4 on a die, it's not going to affect what happens to the coin. So to give you an example of a couple that are not independent. Okay, we're thinking about where the first event would affect the next. So one example here is if we draw 2 cards from a standard deck, whatever happens on the first card, say I draw a king of spades on the first one, well, that means there's one less spade to go around, there's one less card in total, and then it's going to affect my probabilities. Depending on that first card. If the first card isn't a king of spades, well, the king of spades is still in the deck. Say it was a jack of diamonds, well, then one jack is out, one diamond is out, but there are more spades. It's kind of like a Jenga tower. One thing will affect the next. And if we're looking at independence and there's multiple events, this is something we're going to have to consider, even if we're not so much thinking about the word. It's just assigning a word to something that you guys are probably already thinking about when we're looking at multiple events. Okay, last vocab word, and it's kind of a big term, but the concept of it is fairly simple. We're looking at mutual exclusivity, and what that means is that if 2 events are mutually exclusive, it means that there is no overlap. Or in other words, there is the probability of A and B is 0. So meaning if we drew a Venn diagram, you'd have event A over here and event B over here. So one way of thinking about this is if A represents flipping a coin and B represents rolling a standard die, I can't flip and get 6 on the heads. And likewise, I can't roll a die and get tails. That means that they're completely mutually exclusive. There is no overlap. So an example of one that's not so mutually exclusive would be if I want to draw a card from a deck. Let's say we draw that card, and let's say what's the probability that that card is a red or a 7. Well, if I think about this in terms of the problem, in terms of the deck of cards, there are 2 cards that fit both. So it's something I have to consider when I'm working on a probability problem. I have to make sure I don't double count the 7 of hearts and the 7 of diamonds. Both of those would be red. And that would mean that there's not mutually exclusive events happening there. A red could contain some of the 7s, and the 7s could contain some reds. Versus if we're looking at something that is mutually exclusive, I can't have my coin outcome affect, or not affect, but I can't have the same outcome on a die as I can on a coin. And that's what it means to be mutually exclusive. So let's look at how independence, mutual exclusivity, and an OR would affect formulas for calculating probability. So if we're looking at 2 compound events that are independent and mutually exclusive, if we're looking at the AND case, well, then I would multiply. So if I'm looking at the probability of A and B, this would mean I take the probability of A individually times the probability of B individually. And that would make sense. I'm looking at what's the probability that I flip a coin in its tails and I roll a 4 on a die. That means that for every half of the time I flip tails, that means another 1/6 of the time of those halves, I would have another opportunity, or have that many fewer opportunities to achieve success. If we're looking at OR, and they are independent and mutually exclusive, then all we have to do is add the two events. So probability of A individually plus the probability of B individually. So we're looking at that and we're thinking, for example, what's the probability that I flip a coin and it's tails or I roll a 4 on the die? All I need to do is achieve one of them. So there's that part. I also can do both in this case. And since we're looking at if they're not affecting one another, we're fine there. So if we're looking at if things are not mutually exclusive, but still independent, then what we're looking at is the probability of A and B So if we're looking at that, it would still be the same thing. So probability of A and B happening, we still calculate the same way. We do it individually and then multiply them. Okay. Now the kicker comes if we're looking at probability of A or B. Very close to our red equation. We're going to have the probability of A plus the probability of B, and we're going to minus off that overlap. So the reason for this, and we'll talk about an example where this is the case. If I just consider the probability of A, I'm considering the entire portion of A, and if I consider just B, I'm considering the entire portion of B, meaning this stuff in the middle gets counted twice. Hence the subtraction for that part. And the last part, if we're talking about things that are not independent, we have to kind of weigh how one would affect the other. So if two events are not independent of each other, I have to do the probability of A times the probability of B, and I'm going to put a star on that because we have to think about kind of a new norm once A is done. So an example, and we'll talk about an example where this is the case, but for example, if I draw one card out of the deck, well, I've taken one card out, now there's only 51 left in total. And depending on what that card is, there might be fewer spades, there might be fewer sevens, whatever the case may be. And we'll talk about an example where all this comes into play, and these formulas don't necessarily need to be followed to the T. We can just kind of use them as a way to guide our thinking.